Thank you. All right, thanks everyone for joining us for String Fino seminar series this week. Unfortunately, we only have one speaker today, but hopefully that'll be still very fun. Today we have Gonzalo Villa from Cambridge to tell us about cosmic superstrings in large volume compactifications. Please take away, Gonzalo.
Okay, thanks, Monkey. Let me start by thanking you both, Monkey and Mutu, for keeping up with the String Fino seminars. This is a great seminar series. And today I want to tell you about concretely these two works here that I've done with Filippo and Anish. And it fits broadly into this context of cosmic superstring dynamics influenced by displaced moduli that this is a phenomenon that is attracting the attention of some people in our community, and I'm very happy to share it with you today. So what is the idea? Okay. So there are three main ingredients. The main idea of the talk is the observation that moduli dynamics in the early universe influence the physics of cosmic superstrings and their associated gravitational wave spectrum. More concretely, the way how this works is the dimensionless tension of the strings, that is, the tension in Planck units, depends on the expectation value of moduli. You can think of the volume modulus in general, perhaps some conifold modulus if there is warping. If these effective strings are actually wrapped branes, you could think of the sizes of the cycles that are wrapped and so on. And when any of this is dynamical, then the string tension is going to vary adiabatically. And this is going to change the worldsheet dynamics of the string. So let me describe these ingredients. So it's three ingredients that we have. I want to talk a little bit about moduli, a little bit about cosmic superstrings, and a little bit about gravitational waves. So as you know, string theory backgrounds have generic features at low energies. One of them, the important for my talk here, is the presence of gravitationally coupled light scalar particles, which are moduli. They are deformations to certain class of solutions that we are interested in studying. These, as we shall see, can have important implications for early universe dynamics. In particular, as we will discuss, they can alter the equation of state of the very early universe, and they can give rise to physical effects such as variation of fundamental constants. Of course, there is a natural question, which is why should we care about this? If this was to have happened, it should have happened before Big Bang nucleosynthesis, because afterwards were experiments very much constrained the physics of the early universe. And so why should we care about physics in this very unexplored region? And I think the answer to this is that this region of the early universe is unexplored as of yet. And this naturally takes me to my second candidate, to my second ingredient. The idea, of course, is that the universe is transparent to gravitational waves. It always is. Whereas the universe is not transparent to light before recombination, gravitational waves from the very early universe travel essentially non-interacting until our detectors today. And so gravitational waves from the universe should be a natural target for pre-BBN experiments. This observation has attracted a lot of recent attention from a community from a growing community of theorists and experimentalists that are assessing challenges and opportunities that these gravitational waves at high frequencies have. So for cosmological sources, there are two main generic features. First of all, the frequencies tend to be quite large. 10 to the 10 is a good and actually very interesting ballpark. And the observation can be simply related to the fact that, very high energy means very high frequency, or if you want, at very early times, the Hubble radius was very small, and so causality does not allow this physics to source gravitational waves with very large wavelength. The other generic features is that the amplitudes are, of course, very small. This happened very early in the universe, and so the universe has undergone a lot of expansion, which dilutes its signals. But what is very interesting is that they are actually UV sensitive. So very typically, at a given frequency bin, the largest contribution to the gravitational wave spectrum in this bin was sourced from the earliest times. I have to emphasize here that things are actually moving. So this the GravNet collaboration was recently awarded an ERC Synergy grant for searches around of gravitational wave backgrounds around tens of gigahertz, which is this nice, interesting ballpark for cosmological backgrounds. Of course, it is very fair to say that their sensitivities, their expected sensitivities are much lower than we would need in order to probe cosmological backgrounds, but I think it's important to notice that things are moving. And this should make us theorists wonder what are possible sources of gravitational waves. One such source is cosmic strings. Cosmic strings are actually very, very interesting gravitational wave sources, and the reason is as follows. Networks of these objects have an energy density that scales. That is, the energy density in cosmic strings remains a constant fraction of the energy density of the background. So they are never diluted with respect to the background, and so they're always present there. They're always a meaningful contribution to the energy density of the universe, and they so emit gravitational waves, a meaningful amount of gravitational waves at every fold. This in turn implies that the gravitational wave spectrum spans for tens of frequency bins, and every frequency bin is related to a moment in time, as we will discuss later. And so in this sense, the gravitational wave spectrum is therefore a map of the early universe, in the sense that I have the gravitational wave spectrum as a function of frequency. Frequency is related to time, and what happens to the gravitational wave spectrum at any frequency is actually dependent on what the universe was doing at those times. So the spectral index of the gravitational wave spectrum is telling us, or could in principle tell us, something about the equation of state of the universe before Big Bang nucleosynthesis. So that concludes the introduction. Let me tell you about the results, and later on in the talk, I will discuss how one actually reaches these conclusions. What I'm showing here is the gravitational wave spectrum, so the amplitude, the energy density in gravitational waves with respect to that of the background as a function of frequency. And as I was saying, the spectrum spans for tens of frequency beams with a non-trivial amplitude. And what we are seeing here is a history of the universe, really. So for this very flat-looking spectrum, we're seeing the period of radiation domination, which is eventually hit by a period of early matter domination. This is something that these plots assume and that I will discuss later. And something that is interesting is that if moduli, in particular, in this case, if the volume modulus was dynamical in the early universe and changed the tension of these cosmic strings, then the gravitational wave spectrum grows very much at high frequencies with a very large slope. And so this would be a smoking gun signature of this scenario for which moduli are varying. We could see moduli varying through their imprint in the gravitational wave spectrum from these objects. The reason why this goes up so quickly is a consequence of, or is the addition of two factors. If there is more tension, then, as we shall see, the features of the scaling solution is that there is a larger relative fraction of strings, or a larger relative fraction of energy density in strings with respect to the background. And of course, the amount of gravitational waves you source is given by the tension in Planck units. And so the larger the tension, the more gravitational waves you source. In a second scenario, I'm going to assume the simplest version of the large volume scenario. So I'm going to assume that there is a volume modulus that dominates the energy density of the universe and decays gravitationally. And I am going to assume that the recent hints for a gravitational wave background that pulsar timing arrays have observed is explained by a network of cosmic superstrings. And as we will discuss, this implies, or this can be this can be related to the microphysics of the large volume scenario, which in turn gives a prediction for the end of this period of early matter domination, which implies as a tilt in the spectrum in the Lisa band for one free parameter, which I will discuss. Okay, so these are the two scenarios, and in the rest of the talk, I want to discuss qualitatively how one gets to these conclusions. So moduli dynamics very quickly, because I'm sure everyone in this audience knows this story. Let me consider five-dimensional gravity. In the vacuum five-dimensional Einstein's equations admit solutions which are Minkowski times a circle with the circle sense unfixed. I can decompose the metric in this manner and perform a Kaluza-Klein reduction to find that the four-dimensional effective dynamics of this system is that of four-dimensional gravity, some vector field, and this scalar field sigma, which determines the size of the extra dimension, and which at this level of approximation is massless. What is important here is that the expectation values of sigma determines the four-dimensional Planck scale, which is therefore a derived quantity, or the proper frame invariant way of phrasing this is that any energy scale in Planck units will depend on the expectation value of this field. So the takeaway from here is that, okay, these degeneracies to higher dimensional equations manifest themselves at low energies as massless fields, which are these moduli. This is a three-level statement. The expectation value of these moduli parameterize fundamental constants, which in this case is a Planck scale, and will be the idea that I will follow in this talk. And then, of course, once one adds further corrections, then we see that small masses to this moduli are given. So these flat directions are lifted by small corrections. The masses are small, and so you can ask whether they were active in the early universe. And this is what motivates this program. So in particular, by looking at the hierarchy between the electroweak scale and a putative high scale inflation, the fact that there are no free parameters in string theory suggests that inflation actually might have happened very far away from the late time minimum that characterizes the low energy physics that we live in. So the idea is that one has high scale inflation, then and then one must reach this late time minimum. If this is so, then we expect a very interesting cosmology before we began nucleosynthesis. So between inflation and standard cosmology, we could have had a period of kination or kinetic energy domination, a period where the field is still rolling, but Hubble friction induces this tracker regime. And then the field oscillates close to its minimum and gives rise to a period of early matter domination. And what's interesting here is that in this during these epochs, we could have had variation of fundamental constants, in particular, the tension of these strings. So the takeaways, the main points is that the moduli are generic in string vacua. The dynamic is expected to alter the early universe or in the context of what I just said. And so we can get variation of fundamental constants or exotic fluids dominating the energy density of the universe. And so in this talk, what I want to do is to explore how these varying tension effects would affect the dynamics and gravitational wave signatures from cosmic strings. So what are these objects? And these are not necessarily string theory objects. Actually, they were first discussed in the context of field theory. So if one has a symmetry breaking in the early universe whose vacuum manifold has a non-trivial first homotopy group, then these topological defects will generically be formed and form networks, as we will discuss. In string theory, we have similar looking objects, so they could be very highly excited strings, or D1 branes, or wrapped higher dimensional branes. And it is worth noting that we don't have a formation mechanism for this, which would be after-brane anti-grain annihilation, say, after-brane anti-grain inflation. For all that matters today, though, the networks are just described by two parameters, which are their tension in Planck units and the probability that once two of these very highly excited semi-classical objects collide with each other, they actually intercommute, they actually talk to each other, which is given by this intercommutation probability P. And of course, in string theory, there are no free parameters, and so these should be moduli dependent, as is the case in particular realizations. And so what I want to study today is the dynamics of cosmic strings with varying tension. In order to do this, all the objects, all the dynamics of the position of these objects at low energies is described by the number auto action. The number auto action, which in this case will depend in the worldsheet field, in the position field. One can sit down this number auto action and meets two equations of motion. One is very nasty and not particularly informative for current purposes. The other one is an equation for this quantity epsilon. So epsilon is defined in this manner, and it's easy to convince yourself that epsilon times this sigma, where sigma is the special coordinate around the circle, is a proper length. So this is just implementing a boost from the center of mass frame to some point in the worldsheet, and then this quantity times this sigma is the reparameterization invariant way to write the differential proper length. What is important about this equation is that if this quantity here changes sign, well, is that the sign of this quantity here determines whether the proper length of the string decreases or increases. So to make the case, let me consider a cosmology of this form. So this parameter n is just parameterizing the equation of state of the background. And I am allowing for a time dependence, for a power law time dependence of the tension. Then what we find is that for these regimes, for these parameter regimes, the strings actually grow in comoving coordinates. So they grow larger than the scale factor. There are examples in the literature where this has been discussed. More interestingly, volume modulus kination. So if the energy density of the volume modulus falling down a very steep potential is dominating the energy density of the universe, then one can argue that the tension of fundamental strings varies like 1 over time, whereas the equation of state of the universe arranges itself so that this quantity n equals 6, and so this quantity is negative. This means that fundamental cosmic string loops will increase larger, will grow larger than the scale factor. Will grow more fast, more quickly than the scale factor. And this is an observation that has attracted a lot of interest in our community. So the growth of the strings can lead to percolation if these loops grow a lot and they collide with each other, and eventually they can form a network. This can occur not only for fundamental strings, but also for rat brains. You don't need a kinetic background. This has been studied more carefully in this paper. And also something that the growth of the string also can lead to is that they can actually dominate the energy density of the universe, which is a very interesting story. Today, however, I'm just going to assume that there is a network there, and I'm going to explore its phenomenology. So the basic idea is that cosmic strings scale. They track the energy density of the background, as I was saying, and this is a combination of two effects. They dilute more slowly because they are energy distributed through along one dimension. And they do lose energy via intercommutation. So two of these very semi-classical objects collide with each other. They release a loop. This loop oscillates and then emits gravitational waves. And it is this gravitational wave spectrum that we want to compute. What is interesting about this scaling property is that the relative energy density in cosmic strings is proportional to the tension in Planck units. And so if the tension was larger in the early universe, then the relative energy density in these cosmic strings is larger. So you could expect more gravitational waves to be sourced at these very early times. I don't think I have time to talk about this, but the idea is that we can track the dynamics of the loops given some initial conditions that are given by simulations. All of these are moduli dependent. I don't really have time to go into it. I'm just going to tell you what it is that you have to compute. You have to do a computation like this one, where you start with an initial distribution of loops. You redshift this distribution. They emit gravitational waves. Redshift down the gravitational wave, the energy density in gravitational waves today, to find the gravitational wave spectrum. You can sit down, do the computations. What you find is that between certain threshold frequencies, the gravitational wave spectrum just looks like a power law with a power that is computable and only depends on the equation of state of the background and the rate of variation of the tension. It is particularly interesting that if the, thanks monkey, that if the tension is varying, this power is very large, and this is explicitly telling us what we were suspecting, that if the tension is varying in the very early universe, we can expect a very large boost in the gravitational wave spectrum at high frequencies. Of course, there are many uncertainties that I haven't discussed. People in the simulation community are fighting with the dynamics of these networks. I'm just following these people, and if this was not the right way to do things, then we would have to reassess my claims today. So I'm just going to assume that. These are the takeaways. The scaling regime ensures that at every time there is a meaningful fraction of gravitational waves released. There is a one-to-one map between frequencies and times, and so the gravitational wave spectrum is a map of the early universe, which is sensitive not only to the equation of state of the background, but also to variations of the tension, which would be a smoking gun signature of a scenario with rolling moduli. Very, very quickly, just to conclude, let me just tell you that pulsar timing array experiments have evidence for a gravitational wave background at very low frequencies, which would be explained by cosmic superstrings. The Occam-Razor explanation is supermassive black hole mergers, but the spectral index for this is not very well understood, whereas we can do concrete computations for cosmic superstrings and find that the results actually fit well at the moment. We shall see about the future. One can find from here that the tension is very small in string units. The tension is very small in Planck units. And so is the probability of intercommutation, which suggests that we have large hierarchies between M string and M Planck. And this in turn suggests the large volume scenario as a possible embedding. In the large volume scenario, in the most vanilla, simplest version, there are three parameters, which would be the volume modulus, the superpotential, and the string coupling. And the pulsar timing array signal fixes two of these microscopic parameters. This is actually interesting because, again, in the simplest version, I have a period of early matter domination, which ends up in decay and then the standard cosmology, where this volume modulus dominates the energy density of the universe and decays gravitationally. Its decay is given then by the flux superpotential, by the volume, and by the string coupling. Two of these parameters are fixed if we assume that the pulsar timing array observations are explained by cosmic fundamental superstrings in the early universe, and this actually allows us to make a prediction for the tilt of the spectrum. There will be a tilt in the spectrum due to this period of early matter domination. You can sit down and compute, and what you find is that generically this happens in the Lisa band. Okay, so you can vary a little bit the flux superpotential that is not fixed by understanding the pulsar timing array, by explaining the pulsar timing array signals. But what we can infer is that very, very, very typically the slope lies within the Lisa band. And so there is a nice prediction of this very simplified scenario, if you want. And this takes me to my conclusions, I think just on time. So the main conclusion is that cosmic superstrings, well, cosmic strings generally, and perhaps cosmic superstrings, if there are networks of these objects scattered around the universe will be tested in the upcoming years, in particular with the LISA mission. These are very interesting objects, not only because what they are themselves, they are remnants of very UV physics, but they also could in principle provide a window into the physics of the very early universe by doing gravitational wave spectroscopy. Simplified, admittedly simplified UV complete scenarios make, in principle, concrete predictions. For instance, if we assume that this pulsar timing array signal is explained by cosmic superstrings in the large volume scenario, then we have one free parameter which leads to a prediction for the LISA band. And lastly, this variant tension phenomenon predicts spectral indices that cannot be reproduced otherwise in this context. And so if one was to measure this large slope at high frequencies for the gravitational wave spectrum, it would seem like a hint of moduli dynamics in the very early universe. So with this, I conclude, and just thank you so much for your attention.
Let's thank Gonzalo for the very nice talk. Is there any question from the audience? Let me abuse my position and then ask you a question. Maybe you said it already, but it was not clear for me whether or not there is a very clear, suppose that you see some signals or some, gravitational waves from the cosmic strings.
Mm-hmm.
Any signature or any experiments that can really tell us that, okay, this is definitely coming from the fundamental strings or some string ingredients, or it's not really clear how to get the conclusion that it's not an EFT cosmic string?
That's a good question. So often field theory strings, so ordinary field theory strings, I should have said, I think I didn't mention, have this probability of intercommutation equal to 1.
Mm.
So these flux tubes, when they collide with each other, if they collide semi-classically, they will essentially always exchange partners. Whereas for superstrings, this is not the case generically. So in principle, this could be the way to tell. There could be other features. For instance, if one has networks of PQ strings and they form these Y junctions and the low frequency spectrum actually does get features. But for the moment, what seems a way to perhaps conclude or get a hint that this could be explained by cosmic superstrings would be intercommutation probability different than 1, which is what pulsar timing arrays seem to prefer.
Is it a model independent statement, or that depends on models? And then if you pick a very particular model of low energy cosmic superstring, then you get P is equal to 1. Because at the end of the day, you're also using the number go to action to model the cosmic superstring. So in a way, you're still using the low energy FT. So
Yes.
it's rather surprising that the calculation that you do to obtain P can lead to a very different value for cosmic superstring coming from fundamental strings or whatever.
Right. I see what you mean. So, well, I didn't describe the average dynamics, but how this intercommutation probability starts playing a role is in the dynamics of the network. The dynamics of the network for field theory strings is typically obtained from simulations, and it is from these simulations from which you claim that the probability of intercommutation is essentially 1 once they collide. On the other hand, for the cosmic superstring, there are computations that you do perturbatively in the worldsheet. So you conclude that they tend to be suppressed by powers of this string. Does this answer
Yes.
your question? Maybe you want to. Maybe you want a clarification.
I'll ask you after the
Okay.
seminar. Is there any other question from the audience?
Yeah, I have a question, Gonzalo. Can I
Hi, Nacho.
can I just go? Hi, Gonzalo. Nice talk, but I think maybe I missed it, but you have treated all the possible strings, cosmic strings that you find kinda similarly. So usually when you obtain this type of like 4D strings, you can find in some cases ones that are like critical string of some superstring, and others in which is like a wrap brain that generally it's heavier, no? It becomes its tension is much higher, at least in the way it scales. Is there like any implication whether you have some type or the others, or in general they should behave similarly?
Well, yeah, thanks for the question. So, for what I did here, I assume that I have fundamental strings, and this is what allowed me to relate the string tension to the volume modulus, and also to relate the probability of intercommutation to G string. If what you want to describe is the low energy dynamics of the position of the string, I think the number to action should be enough if you neglect things like self-interactions and so on. But to make these calculations concrete, I assume fundamental strings. So for instance, for these values of the volume, if you had a network of G branes, the tension would be larger.
Okay.
I don't know if that's what you were thinking
And
of.
do you think that could affect like possible experimental measurements? Would it be more complicated or
That's a good
less
question.
probable?
Right. This has been studied actually. So there is a recent paper by Anastasios Avgoustidis and Ed Copeland, and I forget the other author, where they do study what happens if you have networks of P, Q strings, which are F strings, D1 branes, and bound
Mhm.
states. And what they find is that the only difference tends to appear at very low frequencies. In particular, let me see if I can move this. In particular, in this side of the spectrum. So it could be interesting if we manage to get farther down with pulsar timing arrays, but I think that's a bit hard. So in principle, there are different observational signatures, and this has been studied. For practical purposes in this particular context, I don't think there is much to say.
Okay, thanks.
But thanks for the question.
Mhm.
All right. Is there another question? If not, let's thank the
There's a
speaker.
question in the chat.
Oh, okay. Should I read out the question?
Yes, please, because I don't know how to open the chat from here.
Okay, great. So it's from Ahmed. Hi, Gonzalo. Thank you for the amazing talk. If one wants to construct the brain anti-brain inflation, in that case, W naught is fixed to match the amplitude of density perturbations, right? My question is, once you require inflationary dynamics, do you lose some tuning freedom of the three LBS parameters that you mentioned?
Right. I see. I see where the question is going to. So, I mean, I tried to take the simplest version of the LBS I could think of, and so in particular, I'm not trying to embed brain anti-brain inflation here. A successful, more satisfactory scenario would take into account modular stabilization during brain anti-brain inflation, the standard model, and so on. I don't know whether adding more ingredients, in particular those two that allow you to stabilize the volume and so on during brain anti-brain inflation, would actually change these conclusions. I would have to think about it. But yes, I think I see your point, Ahmed, that what you want to do is essentially say, okay, in the brain anti-brain story, we found this W0 which would work. So what about what happens if we fix this W0 that would work? The answer is that you will get something in here. So for reasonable values for W0, you typically land in the Lisa band. I don't know if that answers the question.
Good. Then let's thank our speaker again.